So now all those, or this scheme can now be somehow applied. So all possible solutions of the edit distance subsequences can be stored within that matrix we saw here somehow, yeah. And we can apply this this dynamic programming scheme because, as I told you before, a cost minimal path now through this matrix from 0, 0 to nm or from nm to 0, 0 yields the edit distance, obviously. Yeah. So in that case, we go from nm in the matrix. So here is the Q subsequence. No, the Q sequence with n columns, and here is the S sequence with m rows. We go from nm, which is the right lower part here, and we will find a path, cost minimal path, applying these three possible transitions from here to 0, 0, and that's the and this cost minimal path actually is the optimal alignment and determines the costs of this optimal path, which is basically the edit distance, the value of the edit distance. Yeah. So cost minimal path through this matrix from 0, 0 to nm or vice versa yields the edit distance because it's the alignment costs of this optimal alignment. Yeah. You have to be clear that this optimal alignment is not deterministic, so there may be a non-determinism because we may have more than one cost minimal path, more than one optimal alignment. Yeah? And as I said before, the optimal alignment is obtained by backward reconstruction of this path from 0, 0 to nm. So the backward reconstruction starts from nm and goes back in the matrix like the distance itself is defined in a backward manner. Yeah, so it imitates this backward fashion. So the backward reconstruction of the decisions made at every step along the path. Yeah. And the decisions can be stored during matrix construction so that we know also the optimal alignment, of course. Yeah. And here's an example. So the computation of the edit distance with this dynamic programming scheme, and we just highlight here one possible alignment path, and you can see, or you can try to figure out if there are other paths with the same cost actually. Yeah. And you see here you start typically from nm, here from 10, 8, and then you try to minimize the cost by always taking the transition with the minimal cost. And you see that the minimal cost here, or the transition with the minimal cost, is not unique. You can do this way, which is highlighted, or you can also move this way. Yeah. So for example, if you move this way and always at each cell take the transition with the minimal cost, or reducing the minimal cost actually, will guide you on the optimal path, or on one possible optimal path to 0, 0. And in the end, well, you see here that here it's a match. Yeah. So the costs. So the cost here is the cost of the edit distance, so that might be a little bit misleading. So you start here, and you see that if you do this one way, it's a deletion. If you do this way, it's also a deletion in the other way around. And this one here is a match. So you take the match here, and then again you take the match, and then you match O to U. You can go possibly this way, but this way is better later on. Yeah, you can also move this way and go then in this direction, or you can go this way, this way, this way, and so on and so on. Yeah, so there are multiple optimal paths that lead to edit distance of 5 in that case. Okay, yeah, so that's the edit distance, and well, there are a lot of different extensions to the edit distance, especially the so-called weighted edit distance. So you can try to weight edit operations through the use of a ground distance, yeah, that allows to define different costs for insertions, deletions, and substitutions. Yeah, so the weighted edit distance is defined more or less the same way as the normal distance or the normal edit distance, but now you use a ground distance delta that determines the costs of the different operations. Yeah, so for the basic cases, you need the ground or the weighted distance for the insertions, or the deletions, as you will put, which is the symmetric operation, of course. So you take this diamond thing here and determine through this ground distance delta, small delta, the cost for the insertion or the deletion, or the other way around. Yeah, and the same with the second one here, and then for the recursive things, for the recursive cases, it's the same like before, but here again you need the ground distance for a match, and the ground distance for insertions and deletions. Sorry, not for a match, but for a substitution here, of course. Yeah, and depending on the delta, you can weight the substitution and the insertion deletion differently if you want. Yeah. Sorry for that. Yeah, and just a remark, if no insertions or deletions occur, once again, also the weighted edit distance is of course equivalent to the Hamming distance with the particular weight for a match. Yeah? Okay, or for a substitution actually. Yeah. Here's some properties of the edit distance. So the optimal alignment of two sequences is not necessarily unique. We talked about that before. So here you see banana and band, and you see here that we have multiple alignments that have as cost 3. Yeah. So here a substitution, and here's 2 deletions, meaning that the edit and 3 matches. So that the edit distance is 3 here. In this case, again, we have 2 deletions and 1 substitution. The rest is a match, which is also 3. And you'll probably not find a better match or a better alignment of banana and band. So in that case, you see that the edit distance or the optimal alignment is not unique. The edit distance is, of course, but the edit distance is based on the optimal alignment, and the optimal alignment need not to be unique. Nevertheless, the edit distance is a metric. You can even prove that. Not so complex to do. Yeah. Weighted edit distance is also a metric if the ground distance is a metric. Yeah. So then in that case, this delta needs to be a metric. If delta fulfills the metric properties, also the weighted edit distance is a metric. Yeah. Computation time complexity of a single edit distance computation is O of n times m. Given the sequence lengths of n and m. Yeah, so it's a quite costly computation, but on the other hand, it is also a very sophisticated similarity measure. So it takes the alignment into account. So it allows an optimal alignment and not a simple alignment like the Hamming distance. Yeah, and then there, as I said before, are a lot of variants. So once again, a variant here, like you, for example, say that or determine that the first deletion of a symbol can be more expansive than repeated deletions. This is especially important in bioinformatics applications. And then you just have to define a proper weight, a proper ground distance that accounts for weighting first deletions more than consecutive deletions. In that case, usually it's not a metric anymore, but I told you, I think before, in one of the previous and one of the first lectures, that the metric property is somehow a little bit of artificial and is not that of a big problem if distance measures or similarity measures, dissimilarity measures don't account or don't fulfill the metric property. Yeah, so that was the edit distance, and next will be longest common subsequence in the next podcast. See you there, or talk to you there.